This question is about two different types of acid found in organic compounds, carboxylic acids and sulfonic acids, as shown in figure 6.1. Part A. Complete table 6.1 to predict bond angles A and B and name the shapes which make these bond angles in the functional groups of carboxylic acids and sulfonic acids. The first thing to do when you're given a question like this is to work out how many bonding pairs and how many lone pairs each acid has. And then you can work out the shape and bond angle from this information. So if we start with looking at the carboxylic acid and bond angle A, so that has 3 bonding pairs and no lone pairs. So carbon wants 4 bonds, and it has these 4 bonds in the form of a double bond and 2 single bonds. A double bond, a dative covalent bond and a triple bond will all count as one bonding pair, even though there might be 2 or 3 actual bonds. But we have only 3 bonding pairs, which means that the name of this shape is trigonal planar. So that's what we can write in the table. Then we need to work out its bond angle. So trigonal planar shapes have a bond angle of 120 degrees. Then moving on to sulfonic acid. So again, trying to work out how many bonding pairs and how many lone pairs this bond angle will have. So we've got oxygen, and oxygen has 2 sets of lone pairs. And then if we look at its bonding pairs, it's also got 2. So that means that the name of this shape is going to be non-linear. A common example of a non-linear bond would be in water. And non-linear bond angles have an angle of 104.5 degrees. The mark scheme will also accept if you say 104 or 105. But to be more accurate, 104.5 is the better answer, and that's smack dab in the middle of the range that they will accept. So there are several ways that this question is marked. So if you have one row correct, that will be 1 mark, and then another row correct is 2 marks. If you have both bond angles correct, that will be 1 mark, or both shapes correct, that can be 1 mark. So there's 2 ways of getting 1 mark for this question, but to get 2 marks, you need to have all 4 bits of the table correct, so both bond angles correct and both shapes correct. Part B. Ethanoic acid CH3COOH and methane sulfonic acid CH3SO2OH are both monobasic acids. The pKa values are shown in the table. A student suggests that 1.0 moles per decimeter cubed of methane sulfonic acid should have a lower pH value than 1.0 moles per decimeter cubed of ethanoic acid. Write an equation showing conjugate acid-base pairs for the equilibrium of methane sulfonic acid with water, and explain with reasons whether the student is correct. Label the conjugate acid-base pairs A1B1 and A2B2. So there's a lot of information in this question, and to help us out, we're going to break it down. So what the student is suggesting is that methane sulfonic acid will have a lower pH than ethanoic acid. So that's our first statement, and we need to find out if this is correct or incorrect. We need to write an equation showing the conjugate acid-base pairs for the equilibrium of methane sulfonic acid with water. So ethanoic acid being in the table is a slight red herring. We will use it, but for this first bit of the question, we don't need ethanoic acid information. And then we need to explain with reason whether the student is correct and label our conjugate acid-base pairs with these specific labels of A1, B1, A2 and B2. So let's start by writing out equilibrium. If we start with methane sulfonic acid, so CH3SO2OH plus water, and then we have our equilibrium arrow. We need to identify which is the acid and which is the base. So methane sulfonic acid is going to be the acid out of methane sulfonic acid and water is going to be the acid. So we have A1 and then water is going to be B2. So an acid is a proton donor, which means we're going to create CH3SO2O- because it's donated its proton to water, which will produce H3O+. So a base is a proton acceptor. And then if we do the conjugate acid-base pairs, we have B1 and A2. So that's the first part of the question completed. So something to keep in mind is that pKa equals pH. So that helps us with the next part of the question, where we're asked which is the stronger of the two, ethanoic or methane sulfonic acid. So if it's got a lower pH, that means it's going to be stronger, and a higher pH will be more alkaline, so it's going to be a weaker acid. So this is the first statement we can write for this question. So methane sulfonic acid, or CH3SO2OH, is a stronger acid. You could also say that it dissociates more. Either of these are accepted for the first statement. Then we need to tackle whether the student is correct, and the student has said that methane sulfonic acid has a lower pH value than ethanoic acid, which is correct. And that is because it's got a lower pH, a lower pKa value, or you could say it's got a greater Ka value or greater concentration of H+. To get the 4 marks for this question, you get 1 mark for your equilibrium, 1 mark for your conjugate acid-base pairs, 1 mark for saying that methane sulfonic acid is the stronger acid, and then you get your final mark for saying that the student is correct and that methane sulfonic acid has a lower pH or lower pKa value. Alternatively, you could have said that methane sulfonic acid has a higher Ka value or a greater concentration of H+. Either of these would have gotten you the final mark for this question. Part C. Carboxylic acids and sulfonic acids both form esters. Sulfonic acid esters can be hydrolyzed with aqueous alkali. The equation shows the alkaline hydrolysis of a sulfonic ester. In the 3 boxes below, add curly arrows to show the mechanism for this reaction. In the first box, the hydroxide ion acts as a nucleophile. If you're not sure what to do for this type of question, what you should firstly think of is look at the intermediate step and then try and work backwards. So look at what you're trying to produce and then work out where the curly arrows should go based on what you're trying to produce. So we're told in the question that the hydroxide ion acts as a nucleophile. So that helps us with the first curly arrow. We're going to have a curly arrow from the lone pair on the oxygen of the hydroxide ion to the sulfur, and that's going to have a delta positive charge. But we're not asked to put dipoles on, so we don't need to worry about that at this stage. We also know that it should be added to the sulfur or bonding to the sulfur based on the intermediate here. We've got this SOH bond. We also know that we want a negative oxygen, so we're going to have a curly arrow going from the S double bond O, and it's going to go onto the oxygen, and that will produce this negative charge on our intermediate. Then if we look at our next stage, well, we're trying to reform this sulfur-oxygen double bond. So we need our first curly arrow going from the lone pair on the oxygen into the sulfur-oxygen single bond. And then we're also trying to kick off this OCH3- group. So we can have a curly arrow going from the bond of the SO towards the oxygen, and that's going to kick it off as a side group. Then finally, we're trying to lose this hydrogen on the SOH and produce an O-, and then also have as another product HOCH3. So what we're going to do is have a curly arrow from the double bond on the oxygen to the hydrogen, and then from the oxygen-hydrogen bond onto the oxygen, and that will produce this O- charge in our final product, and we'll also get HOCH3. So to get the 4 marks for this question, all 6 curly arrows correct gets you 4 marks. If you got 5 curly arrows correct, that would get you 3 marks. If you got 4 curly arrows correct, that gets you 2 marks. And then 3 curly arrows being correct gets you 1 mark for this question.